Okay, continuing from where we left off in the previous video, we're going through section 1.2 of the geometry textbook, which is talking about informal geometry and measurement. All right, so measuring angles. We just talked about measuring line segments. Now, what about measuring angles? Although we formally define an angle in two sections from now, we consider it intuitively at this time. So, yeah, we're just going to take a purely intuitive, non-official, formal look at what an angle is and how you measure it. An angle's measure depends not on the length of its sides, but on the amount of opening between its sides. In figure 1.16, the arrows on the angle sides suggest that the sides extend indefinitely. So, yeah, the fundamentals of understanding what an angle is, you want to consider that you want to eliminate anything that is completely unnecessary to define an angle. So what is necessary? What do you have to define an angle, to have an angle? What do you absolutely have to have? Well, first, you need two straight sides. They have to be straight. You can't, there's no angle between these two sides. This is you have to be more specific here. What's the angle? This doesn't make sense. I mean, it only makes sense from the standpoint of, like, I guess, where the arrows touch the curved surface. So I guess you could say something like that. But I have to give more information. I need to give you that information. Just as this sits, this doesn't make any sense. So you need straight sides, all right? But then those straight sides, if you extend those straight sides in a certain direction, those straight sides are going to meet at a point. And that point is important for an angle. So, I've got, I've got two straight sides here. All right, that's a start to defining an angle, but this isn't enough. I need to think about, if I extend these two lines in a certain direction, so if you look at here, it's going to be to the left, then I can think about where those sides would eventually meet. Okay, that point is important for defining it, for understanding what an angle is. That's the vertex of the angle. So now with the vertex, now I can start to see and create an angle here, see an angle take shape. Now, what I'm thinking about here is an angle is the amount of separation between these two straight sides from the standpoint of those sides being rotated about that vertex point. You think of that vertex point as a hinge. So the three terms that you need to define an angle at the bare minimum are straight sides, vertex, and rotation. Rotation is an inherent part of what an angle is. That's why you wouldn't ever draw an angle, like the amount of an angle, as a straight line. That doesn't make sense. You always draw it with like a curved line, because you're thinking about that those sides are rotated relative to each other, where they're rotating about the vertex. And it's the amount of opening between those two straight sides is what an angle is. So, okay, you cannot have an angle without a vertex and without two straight sides. And then I guess and an opening between the straight sides. But I guess if there was no opening, that would be an angle of 0. But in general, yeah, there needs to be some sort of opening between the sides based on a rotation of those sides about the vertex. Okay. But they're pointing out here, though, that the length of the sides does not matter at all. The side lengths don't need to be the same length. They can be different lengths. You don't have to have a line segment. Like, yeah, the lines could terminate at the vertex, or they could keep going. It doesn't matter. So again, notice what the bare minimum requirements are to have an angle. And if you want to understand exactly what an angle is, you don't want to add additional information about, you don't need a circle to define an angle, the unit circle, right? We learned that in trigonometry. No. Okay, so an angle's measure does not depend on the length of its sides, but on the amount of opening between its sides. In figure 1.16, the arrows on the angle's sides suggest that the sides extend indefinitely. Exactly. And they don't have to terminate, the sides don't have to terminate here at the vertex. Now, it's not like you couldn't say, if you had this side, these two straight sides, just like that, you could do this and put an angle, and that's fine. That makes sense. But the underlying this is an inherent assumption that if you hypothetically extended the lines, that's where that separation is coming from. It's those lines rotating about a vertex point. So you have to have a vertex to have an angle. You have to have straight sides, and really that's it, because they don't have to be separated, because then you call that a zero angle if they're not separated. But they separate via rotation. Okay, here's another angle. You've got these two straight sides, a vertex, and then there's a separation between the straight sides where you can think about one or both of the sides rotating about the vertex point to create that separation. And it's the amount of separation here is the measure of the angle. Yeah, that's the actual measure of an angle is the amount of the separation there is. The larger the separation, the larger the value of the angle is going to be. The smaller the separation, the smaller the value of the angle is going to be. So we would expect that this angle measure is going to be less than this angle measure, because you can see there's more of a rotational separation between the two straight sides here than here. All right, the instrument shown in figure 1.17 and using the measurement of angles is a protractor. So the parallel to a ruler for the measurement of linear distances, when it comes to angles, is a protractor. But, just like there's different ways of measuring linear distances than just with a ruler, obviously. There's all kinds of ways, but one of the basic ones is for angles, and same with angles, but one of the basic ones is a protractor. For example, we would express the measurement of angle RST by writing, so you put M angle RST. So here, you're just saying, you're pointing out the geometric figure. This is not a number. Angle RST, you're talking about the geometric figure. Here, now you're specifying a measure of that angle. And you can see, all we're trying to do with the protractor is just quantify how much of an opening there is between these two sides. And so all you're going to do is you're going to put the straight edge of the protractor along either side you want, and then it'll give you the amount that's been rotated to get to the other side, and that's going to be the measure of the angle. And it's 50 degrees in this case. But there's different units for angles. You can make angle measure be whatever you want. You can have, just like with lengths, you can come up with different units for lengths. Same with angles. Okay, now they measure the angles in figure 1.16. Let me actually see if I can bring in a protractor. Yeah, there we go. Okay, so let's come to figure 1.16. And, okay, I'm going to scale the size of this up and down. Is that going to affect the angle measure? Well, no, it won't. Think about it. You can think about that on your own of why, if I make this with a ruler, yes. I mean, you can here's a ruler. You can do a demonstration and scale it up or down just for the sake of demonstrating, taking a measurement with a ruler. But for an actual measurement, you can't just scale a ruler, the size of a ruler, up and down. You change the scale, right? Well, think about how with a protractor, you could actually, you could scale a protractor in real life or on the computer screen up and down. And that doesn't affect the measurement of the angle. And one way to look at that, of how that's the case, it's kind of like if you went out front of your house and you pivoted your head left to right to where you looked at the entire span of your house. And let's say you had to pivot your head to the right 15 degrees and to the left negative 15 degrees. Okay. Now it could be the case that if you go out into the mountains and you want to scan an entire mountain range and look over all the way, 5 miles to one direction and 5 miles to the other direction. Well, if you're far enough back, you're only going to have to turn your head plus 15 degrees, minus 15 degrees. So you can see how size in that sense doesn't matter when it comes to angles. So, okay, we take the protractor and we put the straight side here, and let me make it smaller. And let me see if I can, let me try and get a better protractor here. Okay, there we go. Now we can, it's got scales going in both directions here. So you take the protractor and you put the vertex of the angle there's a vertex point on the protractor. Okay, and then you line up one of the sides of the angle with the straight side that's on 0 of the protractor. So you see, this is the 0 line, and here's the vertex point. So you need to do that. You make sure you put the vertex, like this is not the bottom edge of the protractor itself. Like, this is not correct. You can get the wrong angle. Or this is not correct. You have to line up, or like this is not correct. You have to line up the vertex at the vertex point, and then put the 0 line on the protractor in line with one of the straight lines of the angle, and then you can read off this is about 55 degrees. And we could have done it, used either of the sides. So okay, and I mean, you wouldn't do it this way. Well, it's more difficult, but you see, still, it goes from 0 to 55 degrees. Okay, this angle, let's put it at the vertex. And line up one of the straight sides with the 0 line on the protractor, 90 degrees. And there you go. So they got 55 degrees for angle B, 90 degrees for angle 1. Yeah, so they labeled it angle B is 55 degrees, angle N or angle 1 is 90 degrees. Okay, so then they give an example of how to take a measurement with a protractor. We just talked about that. Some protractors show a full 360 degrees. Such a protractor is used to measure an angle whose measure is between 0 and 360. An angle whose measure is between 180 and 360 is known as a reflex angle. So, okay, wait, what? Some protractors show a full 360 degrees. Such a protractor is used to measure an angle whose measure is between 0 and 360. Well, we just took measures of angles between 0 and 360, and we didn't have a full 360 degree protractor, so I'm not sure what they're talking about there. To me, when they're saying an angle whose measure is between 180 and 360, which they're calling a reflex angle, that we would need a full 360 degree protractor. But actually not necessarily. I guess that would be easiest if you had like an angle of 200 degrees. So let me draw this. So here's 200 degrees is about, some amount past 180, that we go from this angle, right? Is what? Well, yeah, I mean, if you had a full 360 degree protractor, I get that would, you could use it to get this angle, but we could still use a regular protractor. Because that the idea is, that going from here to here is 180. So you kind of temporarily extend this line here, and then you do this. Okay, and so from here to here, that's about 32 degrees. So 180 plus 32 is what? 212. So there you go. Approximately. But yeah, I guess it'd be kind of cool to have a full 360 degree protractor you could just read off the measurement straight from the protractor. Just as measurement with a ruler is not perfect, neither is measurement with a protractor. Yeah, so in the units in measurement playlist, you get a sense for the uncertainties of measurements and whatnot. So take a look at that if you need it. That applies to any measurement of any quantity, with an angle, with a protractor, a ruler, thermometer, whatever. There's always uncertainty in measurement, and no measurement that's ever made is perfect. Okay, the lines on a sheet of paper in a notebook are parallel. Okay, so yeah, they're parallel, but are they actually, from the standpoint of the fabric of the universe, are the lines on your notebook parallel? No, they're not even perfectly straight lines, much less parallel. It's the same idea of no measurement is perfect. But yeah, for the sake of discussion in general, yes, they visually, and there's precise machines printing those notebook pages. There you can say they're parallel. So, and what does parallel mean? Informally, parallel lines lie on the same page and will not cross over each other, even if they are extended infinitely. Exactly. So we know that a line, like line AB, extends infinitely in either direction. So if we have another line CD that also extends infinitely in either direction, the idea is you could follow either one of those lines infinitely far in either direction, and it will never cross over the other line. And if that's the case, then that means line AB is parallel to line CD. But that's an informal definition. To me, it's a really good one, but it's still informal. Okay, we say that lines L and M in figure 1.19a are parallel. Note here the use of a lowercase letter to denote a line. Yeah, we can do that. We say that the line segments are parallel if they are parts of parallel lines. So if line RS is parallel to line MN, then segment RS is parallel to segment MN. So yeah, if we come here, you can say that segments are parallel. However, you want to be careful here, because I could say, okay, I've got segment AB and segment CD. Well, they don't cross, so they're parallel. No, you have to think about it from the standpoint that segment AB, if it was part of a line, so, okay, and then segment CD was also a part of a line. From the definition of parallel lines, are those two lines parallel? If they are, then you can say segment AB is parallel to segment CD. Okay, and so let's see, lines L and M are parallel. You can visually think about this. You go infinitely far down line M or line L, and you'll never touch line M. If you go infinitely far up or down line L, no matter how far you go, you'll never touch line M. That means those two lines are parallel. Because you could say the same thing about if you go infinitely far down line M, you're never going to touch line L. And then here, these two segments are parallel, because if you thought about the corresponding lines to these segments, those two lines are parallel. Okay. For set A is equal to 1, 2, 3, and set B is equal to 6, 8, 10. Looks like we're changing gears here, coming to like a new topic. There are no common elements. For this reason, we say that the intersection of A and B is the empty set. So, okay, we have set A and set B. If we want to think about the intersection of set A and set B, well, that set is empty. There is no intersection, and so that would be equal to this. It's called the empty set. Now, note that what would set A union set B be? Well, that wouldn't be the empty set. That would be 1, 2, 3, 6, 8, 10. That would be this set. Set C, not the empty set. Okay? Just as A intersection B is equal to the empty set, the parallel lines in figure 1.19 are characterized by L intersection M is the empty set. So yeah, they're talking about here, we can use this set notation in other contexts. You know, when it came to statements, the truth of statements, we could use the set notation. We could represent a statement by as a letter. Statement P and statement Q could be compared with set notation. Well, they're pointing out here that we can also do this with shapes and figures. We can think about the intersection of here we're thinking about two lines. But when it comes to parallel lines, the intersection is empty, the empty set. Okay, in figure 1.2, the sides of angles ABC and DEF are parallel. So yeah, the segment AB is parallel to ED, segment CB is parallel to segment EF. Use a protractor to decide whether these angles have equal measures. So that's interesting. It looks like they will. So just past 40 degrees, and then just past 40 degrees again. So yeah, both measure about 44 degrees. Okay, that's interesting. We might be able to prove at some point that if you have the two separate angles and the straight sides of those angles are parallel, you know, there's two that are parallel and then the other two are parallel, then the angles are going to have equal measure. Can't state that officially. We just did some inductive reasoning with the protractor to make a suggestion, an intuitive statement, but maybe we can make a deductive statement later. Okay, two angles with equal measure are said to be congruent. In figure 1.20, we see that angle ABC is congruent to angle DEF. So yeah, they're saying that two angles that have equal measure are said to be congruent. And if to think about that, so okay, we want to take the shape and you can change its orientation, but not change its size. And as long as they line up and it's a perfect match, they're congruent, right? Now, but what if we line these up? Let's say we made segment BC a lot longer. And then you put these on top of one another, and all of a sudden these two sides don't line up perfectly. So the angles are still congruent? Yes, they are, because when it comes to an angle, the side lengths don't matter. You just can't change the fundamentals of what you're saying is congruent as far as the size goes. In other words, you can't change the degree. When it comes to size, you can't change the degree of rotational separation between the sides. Then you've changed the shape, the figure. So as long as all you need with an angle is two straight sides, that's it. And you can scale that angle, reorient it, whatever, as long as you don't change the degree of opening between the straight sides. And when you line them up, the two straight sides need to line up perfectly. It doesn't matter if their lengths are the same, who cares? As long as the two straight sides line up perfectly, once you put the vertexes on top of one another, then the angles are congruent. Okay, in figure 1.21, angle ABD has been separated into smaller angles ABC and CBD. If the two smaller angles are congruent, so they have equal measures, then angle ABD has been bisected. Okay, so we started with an angle ABD. That's where we started. Okay, imagine BC isn't there. We start with angle ABD. If we draw another straight side to where we separate angle ABD into two separate angles, we cut it into two separate angles. If the measure of those angles, if those two angles are congruent, which also means that the measure of the angles is equal, kind of like with line segments, if the measure of the line segment, the lengths of two line segments are equal, then those segments are congruent. Then this angle ABD is said to have been bisected. It's kind of like this is like the parallel to the midpoint of a line segment. You put a point to where in the middle of the line, between the two endpoints of the line segment, to where the length of from the first point to the point, that middle point, is the same as the length from that middle point to the other point, then you've said that's the midpoint of the line segment. You've cut the line into two equal pieces. Well, similar idea here. If you separate an angle into two separate angles, and those two angles have same measure, or they're equal, or they're congruent, then you've said to have bisected that angle. So angle ABD has been bisected. It means it's separated into two separate angles. that have equal measure, that are congruent. Similarly, the word trisect means that the line segment or angle is separated into 3 parts of equal measure. Oh, yeah, so we can use this term bisect and trisect with a line segment as well. So if you put a point in between the two endpoints of a segment, that's at the midpoint, then you've bisected that line segment. And so you can use that term with angles or lines. And trisect means the same thing. You cut it into 3 equal angles or 3 equally length lines. So you would need 2 points to do that with a line segment, and you need to put 2 straight sides to trisect an angle. All right, any angle having a 180-degree measure is called a straight angle, an angle whose sides are in opposite directions. Okay, the sides are in opposite directions. You have a side going one way, there's the vertex, and then a side going the opposite direction. That's the other side. That's a straight angle. It has measure 180 degrees. When a straight angle is bisected, as shown in the figure, the 2 angles formed are right angles. Right angles means the angle measures 90 degrees. Okay, so here's a straight angle. The 2 sides go in opposite directions. There's with the vertex at the middle, 180 degrees. If you bisect that angle, so you have to bisect it, you need to bring in another straight side. So, and you're going to put a straight side out from the vertex to where it separates that angle into 2 equal angles. When you bisect a straight angle at 180 degrees, that means you have 2 90-degree angles. Those are called right angles. Okay, when 2 lines have a point in common, as in this figure here, they are said to intersect. When 2 lines intersect and form congruent adjacent angles, they are said to be perpendicular. In figure 1.23, lines R and T are perpendicular if angle 1 is congruent to angle 2, or angle 2 is congruent to angle 3, and so on. So, okay, if you have 2 lines that have a point in common, so that means they're not going to be parallel. That means those lines intersect. So if you have 2 lines that aren't parallel, if they're not parallel, then 100% that means they're going to intersect somewhere. Now, if when they intersect, they form congruent angles, so, that doesn't have to happen, right? What they're talking about is you have this line here, they intersect, and you're thinking about, okay, this angle and this angle. Are those 2 angles congruent? And kind of same idea over here. You could, A, B. Are those 2 angles congruent? Well, in this case, no. So, but if they're congruent, though, then it's going to be right angles then. If these 2 angles were congruent, then that means they're going to be 90 degrees. And you can kind of get a sense of why that is, because the total amount you're adding from, this total angle is 180. So if the 2 angles are going to be congruent, they have to be 90. Now, what is the angle, just a mental exercise here, what is the angle between two parallel lines? Well, there is no angle. And why is there no angle? You might say, oh, is it 90 degrees or it's 180 degrees? No, there is no angle. Why not? Because you're missing one of the fundamental features that are needed to have an angle. The absolute basic fundamental features. You're missing it. Remember, you have to have straight sides, 2 straight sides. We've got that, okay. But then you have to have a vertex, a point where you can extend those sides in one direction, and those lines meet. And that's what you're thinking about, the separation. Like, there is separation between these lines, but remember, a key word with an angle is rotational separation. It's a rotation about the vertex. So there's no vertex here. So this separation is not rotational. So there's no angle here. There's no common point of intersection that's a vertex. So there's no angle. The lines, the straight sides have to intersect. And since parallel lines don't intersect, there's no angle. All right, in figure 1.23, suppose that angle 3 is congruent to angle 4, and then also angle 1 is congruent to angle 4, angle 1 is congruent to angle 3, or lines R and T perpendicular. So let's see. So if angle 3 is congruent to angle 4, are these lines perpendicular? Yes, because the idea is the sides are going to form these congruent adjacent angles. So you're going to be bisecting 180. So if angle 3 is congruent to angle 4, then angle 3 and angle 4 must be 90 degrees. It's perpendicular. Really, if any of these angles are congruent, then you can state that that the lines, the intersection of the lines, they're perpendicular. Because once you say that one angle is congruent to the other angle, like we said angle 1 is congruent to angle 3. Well, actually, no. If you said angle 1 was congruent to angle 3, you still could have a case where angle 4 is congruent to angle 2, but they're not perpendicular. It needs to be that you say angle 1 is congruent to angle 2, or angle 4 is congruent to angle 3, then the lines are perpendicular. Because you've got, if angle 1 is congruent to angle 2, then since you have a straight angle here, then angle 1 and angle 2 must be 90. And same idea here. They're saying that the two lines intersect, and like the bisection makes congruent angles. So like we're thinking about the bisection here. You have, so here's the point in that now this angle, this side bisects this straight angle here because the two angles are equal. Then they're perpendicular. This is, you know, we're thinking about comparing this angle to this angle. We're not talking that that's beyond the scope of what we're talking about here. We're talking about like the idea of you formed two adjacent angles here by the intersection that are the same. Well, because we have two lines here that those angles it's going to be bisecting a 180 degree angle, making right angles. They're going to be perpendicular. But if side 1 and 2 or angle 1 and 2 are congruent, then angles 4 and 3 are going to have to be congruent and also 90, because this line doesn't all of a sudden change direction when it crosses over, right? It's not like when you cross over to the other side that this line and this line change orientation. No, it's the same thing. So these are going to be congruent. This is going to be bisected as well.